Something unusual entered our solar system, and it did not behave like a routine visitor. The data did not arrive as faint hints or marginal anomalies. It arrived as a clear, measurable deviation from what decades of observation have taught us to expect. Astronomers identified the object as 3I Atlas. Its trajectory confirmed an interstellar origin, meaning it was not bound to our Sun but instead passed through from another star system. Such objects are rare but not unprecedented. What distinguishes this one is not its path, but its composition. Using observations from the James Webb Space Telescope, multiple research teams analysed the material released from this object. Their methods differed slightly, but their results converged on a single point: the presence of an unusually high concentration of a specific isotope. That isotope is deuterium. At a basic level, deuterium is a form of hydrogen. It contains one proton and one neutron, instead of just a proton. This small structural difference does not change its chemistry significantly, but it changes its physical behavior in measurable ways. In particular, it becomes highly relevant in environments involving nuclear processes. Now here is the important detail: the measurements were not disputed. Independent teams working with separate datasets and analytical models arrived at values that were consistent with each other. In science, this kind of agreement usually strengthens confidence in the observation itself. The uncertainty lies elsewhere. It lies in interpretation. What does it mean for an interstellar object to carry such an unusual isotopic signature? Is this a natural outcome of some extreme environment, or does it point to conditions we have not yet fully understood? This is where careful thinking becomes essential. In scientific inquiry, data and explanation are not the same. Data tells us what is observed. Explanation attempts to tell us why. At this stage, we have reliable data. What we do not yet have is a reliable explanation. To move forward, we must first understand why deuterium, among all possible elements, carries such weight in this discussion. That requires us to examine its role not just as a chemical substance, but as a key component in some of the most energetic processes known to science. To understand why this isotope matters, we must look beyond its definition and examine what it enables. Hydrogen, the most common element in the universe, consists of a single proton. Deuterium carries an additional neutron. This small structural change does not significantly alter its chemistry, but it becomes critical when we enter the domain of nuclear physics. In chemical reactions, atoms rearrange and release modest amounts of energy. In nuclear reactions, the nucleus itself changes. Deuterium is central to one of the most efficient of these reactions: fusion. When it combines with tritium, it forms helium and releases a large amount of energy. This process is already used in thermonuclear weapons and is being developed in controlled systems such as ITER and the National Ignition Facility. To understand the scale, consider rainfall. A single drop has no visible impact. Even a brief shower changes little. But when millions of drops accumulate, they can flood entire streets and disrupt a city. Chemical energy works in a similar way. It is released in small, distributed amounts, requiring continuous input to sustain large systems. Fusion changes this entirely. It compresses what would be millions of small releases into a single, concentrated event. This is why even a small quantity of deuterium can have a large effect. A mass no larger than a suitcase, if fully engaged in fusion, could release energy on the order of tens of kilotons of TNT. To make this concrete, that level of energy is comparable to what could significantly impact an area of several square kilometers. In practical terms, a densely populated urban region, such as parts of Manhattan in New York City, could experience widespread structural damage within that radius. The quantity remains small, but the impact spreads outward because the energy is densely concentrated. There are further implications. At such high energy levels, materials do not simply burn, they can vaporize. Air expands rapidly, creating pressure waves, and electronic systems can fail under intense energy exposure. These effects follow directly from known physical principles. Here is a useful teaching insight. When a material combines rarity with extremely high energy potential, its presence is never neutral. It indicates either stored energy or conditions capable of generating and sustaining that energy. This is why the concentration of deuterium becomes important. It is not merely a chemical variation, it is evidence of processes operating at an unusually high energetic scale. With this understanding, the measurements from 3I Atlas are no longer just numerical observations. They begin to point toward conditions that require deeper and more precise investigation. With that framework established, the measurements begin to take on a more precise meaning. The question is no longer what deuterium is, but how much of it is present, and how that compares to known cosmic standards. On March 6, 2026, an international research team analysed water vapour emitted by 3I Atlas. This was not a surface observation. It relied on spectroscopic data, where light is separated into its component wavelengths to identify chemical signatures. From this, they measured a specific ratio, deuterium to hydrogen. Now, to interpret any ratio, we require a reference point. In Earth's oceans, the ratio is approximately 1 in 6,500. This value is not arbitrary. It reflects billions of years of planetary formation, chemical cycling, and isotopic stability. Even across different environments on Earth, this ratio remains relatively consistent. When we look beyond Earth, comets provide the next comparison. These are considered relatively primitive objects, often preserving early solar system material. In most comets, the ratio ranges between 1 in 5,000 and 1 in 10,000. While there is variation, it remains within a narrow and predictable band. Now consider the measurement from 3I Atlas. The ratio was recorded as 1 in 100. To understand how large this difference is, focus on the scale of change. The shift from typical cosmic values to 1 in 100 is not incremental. It represents an increase of tens of times beyond known ranges. At this level, the system no longer fits within established patterns and must be treated as fundamentally different. A teaching insight is useful here. In scientific data, small deviations suggest noise or local variation. Large deviations, especially those exceeding an order of magnitude, indicate a fundamentally different process. This measurement does exactly that. It does not extend the known distribution, it breaks away from it entirely. Importantly, the data itself was not treated casually. It was logged, analysed, and submitted for peer review. Independent verification is a standard requirement before any claim of this magnitude is taken seriously. The researchers followed that process, so we arrive at a clear position. The measurement is credible, the comparison is well established, and the deviation is extreme. At this point, the discussion shifts. The focus is no longer whether the value is correct, but what conditions could produce such an enrichment in water. And just as that question begins to take shape, a second independent measurement introduces a new layer of complexity. That question becomes more complex when a second independent measurement is introduced, not from water, but from an entirely different molecule. On March 24, 2026, another research team analysed methane released from 3I Atlas. The method remained consistent in principle, using spectroscopic data to determine isotopic composition. However, the substance under examination had changed, and this distinction is important. Methane forms under different physical and chemical conditions than water. It is more sensitive to temperature, pressure, and formation history. Because of this, measuring deuterium within methane provides an independent line of evidence. It allows researchers to test whether the earlier observation was specific to one compound or reflective of the object as a whole. The result was measured at 3.31%. To interpret this value, we again rely on established comparisons. In Comet 67P, one of the most studied comets in recent history, the deuterium fraction in methane is approximately 0.24%. In gas giants such as Jupiter, it is closer to 0.01%. This places 3I Atlas at roughly 14 times higher than Comet 67P and nearly 300 times higher than Jupiter. A teaching insight follows from this comparison. When two independent measurements, derived from different molecules and formation pathways, both indicate extreme enrichment, the likelihood of measurement error decreases significantly. The observation begins to shift from anomaly to pattern. This is precisely what we see here. The first measurement established an outlier. The second confirms that the outlier is not isolated. It is important to recognize what has now changed. we are no longer dealing with a single unusual value in a specific context. We are observing consistent behavior across multiple chemical systems. In scientific analysis, this is a critical threshold. A single data point can be questioned. A repeated pattern, especially across independent methods, demands explanation. At this stage, the focus turns toward origin. What kind of environment or sequence of processes could produce such consistent enrichment across different molecular structures? The initial response from researchers was to propose a natural explanation. It is a logical step grounded in known physical principles. However, as we move forward, that explanation introduces a constraint that cannot be ignored. At this point, the evidence establishes a consistent pattern. The next step is to explain it. The research teams proposed a natural mechanism grounded in known physics. The key idea is isotopic fractionation, a process where certain isotopes become more concentrated under specific environmental conditions. In this case, the condition is extreme cold. Below approximately 30 Kelvin, which is about minus 243 degrees Celsius, chemical reactions begin to favor the incorporation of deuterium over ordinary hydrogen. At such low temperatures, molecular interactions slow down, and heavier isotopes become more stable within compounds like water and methane. This provides a plausible pathway. If 3 I-Atlas formed in an environment that remained consistently below this temperature threshold, it could gradually accumulate higher concentrations of deuterium over time. From this reasoning, researchers extended the timeline. They proposed that the object formed between 10 to 12 billion years ago, in an ancient and extremely cold region of the galaxy. This would place its origin well before the formation of our Sun, making it a preserved fragment from an earlier phase of the Milky Way. A useful teaching insight emerges here. In astrophysics, age is often inferred indirectly through conditions. If an object shows signatures that require specific environments, scientists work backward to identify when such environments could have existed. In this case, the argument is clear. Extremely low temperatures enable fractionation. Sustained exposure to those temperatures over long periods leads to enrichment. Therefore, an ancient and cold origin appears consistent with the observed data. There is also an important implication. If this explanation holds, then 3 I-Atlas is not just unusual. It is a time capsule. It preserves chemical information from a period of the galaxy that is otherwise difficult to study directly. However, scientific explanations are not evaluated on plausibility alone. They must also satisfy known constraints. And this is where the proposed model begins to encounter a limitation that cannot be overlooked. That limitation becomes clear when we examine a constraint that comes not from chemistry, but from cosmology itself. Avi Loeb identified a direct contradiction within the proposed explanation. The argument for extreme deuterium enrichment depends on formation at temperatures below 30 Kelvin. This threshold is not arbitrary. It is the point at which fractionation strongly favors deuterium over hydrogen. However, we must consider the conditions of the universe at the time this object was said to form. Roughly 10 to 12 billion years ago, the universe was warmer than it is today. The cosmic microwave background, which acts as a baseline temperature for all of space, was approximately 30 Kelvin at that epoch. This detail is critical. The cosmic microwave background is not a local condition, it is universal. It sets the minimum possible temperature across all regions of space at a given time. A useful teaching insight follows from this. While local environments can become hotter due to stars or other processes, they cannot become colder than the background temperature of the universe itself. That lower limit is fixed by cosmology. Now we arrive at the contradiction. The proposed explanation requires temperatures below 30 Kelvin to produce the observed enrichment. But at the time of formation, no region of the universe could cool below approximately that same temperature. Both statements cannot be true simultaneously. This is not a minor discrepancy. It is a boundary condition. When a hypothesis violates a known physical limit, it cannot be accepted without modification. At this point, the discussion shifts again. The natural explanation is not dismissed entirely, but it is no longer sufficient on its own. It leaves a gap between what is required and what is physically allowed. Loeb then posed a question that follows logically from this gap. If natural processes cannot fully account for the observed enrichment under known constraints, could the origin involve processes that are not purely natural? He did not provide an answer. The question remains open, and in science, such questions are often more important than immediate conclusions. What matters here is not speculation, but recognition. The data now conflicts with a key physical limit, and that conflict must be resolved. As we move forward, it becomes clear that the anomaly is not confined to composition alone. Additional observations begin to challenge our understanding in entirely different ways. The inconsistency is no longer limited to composition. It now extends into motion, where the behavior of the object departs from established physical models. Comets are not passive bodies. As they approach a star, heat causes volatile materials to sublimate, producing jets of gas. These jets act like small thrusters, generating what is known as non-gravitational acceleration. Over time, this effect slightly alters the trajectory of the object. Importantly, this process is well understood. Given the rate of outgassing and the orientation of the jets, scientists can predict both the magnitude and the direction of the resulting acceleration with reasonable accuracy. In the case of 3I Atlas, those predictions do not match observation. The object does exhibit non-gravitational acceleration, but the direction of that acceleration is inconsistent with what outgassing models require. Instead of being pushed in a direction aligned with expected jet activity, it moves along a vector that current models cannot reproduce. A useful teaching insight emerges here. In physics, when both magnitude and direction can be predicted, agreement with observation strengthens the model. When either deviates significantly, it signals that an underlying assumption may be incomplete. Here, the deviation is not subtle. Adjusting parameters such as jet intensity or distribution does not resolve the discrepancy. The mismatch persists across simulations and independent analyses. This leaves two broad possibilities. Either the mechanism driving the acceleration is not standard outgassing, or there exists an additional influence that has not been accounted for. It is important to approach this carefully. The presence of an unexplained force does not immediately imply a new form of physics or a non-natural origin. It indicates that the current model does not fully describe the system. However, when combined with the earlier anomalies in composition, the situation becomes more complex. We are no longer examining a single irregularity, but a pattern of deviations across different domains. At this stage, classification becomes uncertain. The object shares characteristics with known cometary bodies, yet it does not conform to their expected behavior. As we continue, the focus shifts again, this time from motion to structure. The way material is emitted from the object introduces another layer that must be examined with equal precision. That shift in focus reveals a new layer of structure, one that is not defined by composition or motion, but by how material is released over time. Observations of 3I Atlas identified 3 distinct jets emitting from its surface. In isolation, jets are not unusual. Comets regularly produce them as volatile materials escape under solar heating. What matters here is not their presence, but their arrangement. In typical cometary bodies, jets appear irregular. They vary in strength, direction, and timing, depending on surface features and rotation. There is no requirement for symmetry, and in most cases, none is observed. In contrast, the jets from 3I Atlas display a high degree of symmetry. They are positioned in a balanced configuration, suggesting a level of structural consistency that is not commonly associated with natural outgassing. A teaching insight is useful at this stage. In natural systems, irregularity is common because formation processes are chaotic. Symmetry, especially repeated symmetry, often indicates constraints or internal organization guiding the outcome. This observation alone does not provide a conclusion, but it raises a question. What mechanism could produce and maintain such balanced emission patterns over time? The answer becomes more complex when we consider temporal behavior. The object exhibits a repeating brightness variation with a period of 16 hours and 10 minutes. This signal is not random. It remains stable across observations, indicating a consistent underlying process. In most rotating bodies, brightness variations arise from uneven surfaces or changing reflective properties. These typically produce irregular light curves, with fluctuations that shift over time. Here, the periodic signal remains precise and repeatable. It does not drift or degrade, which suggests that the source of variation is not purely surface irregularity. A useful comparison could be made with mechanical systems. When a process repeats with consistent timing, it implies control or stability in the underlying mechanism. In natural rotational systems, such precision is less common unless specific conditions are maintained. At this point, two features must be considered together: symmetric jets and stable periodic signals. Each is unusual on its own. Together, they suggest a level of structural and temporal organization that does not align easily with standard comet models. This does not immediately redefine the object. However, it narrows the range of viable explanations. Any model must now account not only for composition and motion, but also for consistent structural behavior over time. As the analysis continues, attention shifts once again, this time toward the material being released itself, and what it reveals about the processes occurring within the object. That final layer shifts attention from structure to the nature of the material being released, and here the observations become even more difficult to reconcile with standard models. Spectroscopic analysis of the emissions from 3I Atlas identified vaporized iron and nickel. These are not volatile substances. Under normal cometry conditions, materials such as water, carbon dioxide, and methane sublimate easily. Metals like iron and nickel do not. To transition these metals into a gaseous state requires extremely high temperatures. In typical comet environments, such temperatures are not sustained at the levels needed for continuous metal vaporization. This creates a clear mismatch between expected thermal conditions and observed composition. A useful teaching insight can be drawn here. In planetary science, the type of material observed in emissions often reflects the energy available within the system. Low-energy environments release light, volatile compounds. High-energy environments are required to release heavier, more stable materials. In this case, the presence of vaporized metals suggests that processes within or around the object are operating at significantly higher energy levels than standard cometary activity would allow. This observation does not stand alone. It aligns with earlier anomalies in composition, motion, and structure. Each independent line of evidence points toward conditions that are not easily explained within a single natural framework. At the same time, there is an additional dimension to consider, one that lies outside direct physical measurement. A Freedom of Information request submitted to the Central Intelligence Agency received what is known as a GLOMAR response. This type of response is used when an agency neither confirms nor denies the existence of relevant records, typically in cases involving sensitive or classified information. A teaching clarification is important here. Such responses are not part of scientific analysis. They do not constitute evidence about the object itself. However, they do indicate that the subject has reached a level of institutional attention beyond routine astronomical observation. This introduces a parallel consideration. While the scientific community focuses on measurement and explanation, other institutions may evaluate the same data through different lenses, including security and strategic relevance. At this stage, the situation becomes layered. We have high-energy material behavior that challenges physical models, and we have institutional signals that suggest the data is being treated with caution. Neither of these elements provides a definitive conclusion, but together they expand the scope of the investigation beyond a purely academic question. As the object continues its trajectory out of the solar system, one final issue remains unresolved, not about what was observed, but about when it was first seen. That uncertainty extends to the very beginning of our observation timeline, raising a final question that is not about composition, motion, or structure, but about detection itself. 3I Atlas was officially identified on July 1st, 2025. This date marks its recognition as an interstellar object within the scientific community. However, archival analysis reveals that it had already been observed nearly 2 months earlier by the Transiting Exoplanet Survey Satellite, commonly known as TESS. This creates a gap between observation and recognition. A teaching insight is useful here. In astronomy, detection and identification are not always simultaneous. Instruments collect large volumes of data, and objects are often identified only after detailed analysis. However, when dealing with unusual objects, the timing of recognition can influence how quickly follow-up observations are initiated. In this case, the delay remains unexplained. It is not clear whether the object was overlooked, misclassified, or simply not prioritized at the time of initial detection. As the object continues its trajectory away from the solar system, this gap becomes more significant. Unlike planets or recurring comets, interstellar objects do not return. Once they leave, the opportunity for direct observation is effectively lost. NASA is now consolidating all available data into a centralized archive. This is a standard approach when dealing with transient phenomena. The goal is to preserve every measurable detail for future analysis, even after the object itself is no longer accessible. At present, only 3 interstellar objects have been observed passing through our solar system: Oumuamua, Borisov, and 3I Atlas. Each has provided limited data, constrained by the brief window of observation. For 3I Atlas, the challenge is not the absence of data, but the absence of a unified explanation. We are left with a set of observations that do not converge into a single model. The deuterium levels exceed known limits. The proposed formation conditions conflict with cosmological constraints. The motion does not align with established mechanisms. The emissions display structural symmetry and temporal stability. The material composition indicates high-energy processes that are not easily explained. A final teaching reflection follows. In science, unanswered questions are not failures. They are indicators of where current understanding reaches its limits. 3I Atlas represents such a limit. The data has been collected, verified, and preserved. What remains incomplete is the interpretation. And so the conclusion is not a resolution, but a boundary. The data exists. The interpretation does not.